Good morning, friends. My name is Neha Saunke, and today I will tell you about clock synchronization in distributed databases. Synchronization in distributed database is often much more difficult than synchronization in uniprocessor or multiprocessor systems. In centralized system, time is unambiguous. Whenever a process wants to know the time, it simply makes a system call and the kernel tells it. If process A asks for time and then a little later process B asks for time, the value that B gets will be higher than the value A got in centralized systems. Whereas in distributed databases, time is ambiguous. We know that distributed databases have different machines where each machine has its own clock and the time along each machine may vary. In distributed system, achieving agreement on time is not trivial. Let us see why clock synchronization is important in distributed databases. For example, in centralized systems, a program named program, which is a large program split into multiple source files, where change to one source file requires only that file to be recompiled and not all other files. The way sample program runs is simple. When the programmer finishes changing all the source file, he starts sample program, which examines the time at which all the source file and the object files were last modified. If the source file has time 2031 and object file has time 2030, which means that the source file has been changed since object file was created first, and thus the modified source file must be recompiled. On other hand, if source file has time 2031 and object file has time 2032, it means that nothing is changed and nothing has to be recompiled. This was all about centralized system. Let us see how this occurs in distributed systems. For example, there is a distributed system where the compilation and addition of programs are held on different machines, each with its own clock. And suppose the object file has time 2144 and source file is changed but the time is 2143 on the machine on which the file is modified, has a clock that is running late. Thus here the sample program will not know about the changes in the file and thus no file will be recompiled. Thus the program will probably crash. Hence clock synchronization in distributed databases is necessary. Now physical clocks. What is actually a clock? All computers have a circuit for keeping track of time, which is called a clock. Timer is perhaps a better word. A computer timer is actually precisely machined quartz crystal, which when kept under tension, quartz crystal oscillates at a well-defined frequency that depends on the kind of the crystal, how it is cut, and the amount of tension applied on the crystal. Each crystal has two resistors, one counter resistor and another is holding resistor. On oscillation of the crystal, it decrements the counter by 1. When the counter gets to 0, an interrupt is generated and the counter is reloaded from the holding resistor. In this way, it is possible to program a timer to generate an interrupt 60 times a second or at any other desired frequency. Each interrupt is called as one clock tick. With a single computer and a single clock, it does not matter if this clock is off by a small amount. Since all the processes on the machine use the same clock, they will still be internally consistent. As soon as multiple machines are introduced, each with its own clock, the situation changes. There are different algorithms which helps to keep the clocks in different machines synchronized. The first algorithm is the Christian's algorithm. This algorithm is based on the work of the Christian in 1989. Christian algorithm works between a process P and a time server S, which is connected to a source of UTC. UTC is a universal coordinated time. Periodically, each process P sends a message to the time server asking for its current time. The server then responds as fast as possible with a message containing its current time T. When the sender process receives the reply, it can just set its clock to CUTC. But sometime might be required for processing the response. So P sets its time to T, which is a response sent by the time server. Time server T plus RTT by 2, where RTT is the round trip time, that is T1 minus T0. Here RTT is assumed to be split equally into request and response, which may not always be the case. Hence, to improve accuracy, Christian suggested making more than one request to more than one request to the server and asking the response and using the response time with shortest round trip time. Another option is to consider the time required by the time server to handle the interrupt and processing the request called interrupt handling time. P sets its time to T plus RTT by 2, but now here RTT is T1 minus T0 minus I. This figure depicts the process of asking time to the time server. Here client process sends request to the time server at time T0 and the time server takes I time in handling the interrupt. And finally at time T1 the process P gets its reply. And finally its clock sets its clock to T plus RTT by 2, where RTT is calculated as T1 minus T0 minus I. The next algorithm is the Berkeley algorithm. We know that in Christian algorithm, the time server is passive and other machines periodically ask it for the time. Here in Berkeley algorithm, the time server is active and polls every other machine to time to ask what time is there. Here the time server is actually a master which is chosen via election algorithm. The master polls the slave and the slaves reply with their time. The master then observes the RTT of the message and estimates the time of each slave and its own. The master computes an average time and tells all other machines to advance their clock to the new time or slow their clocks down until some specified reduction. For example, let us see the figure. For example, in the figure, at 3 o'clock, the time daemon, which is a master, tells the other machines its time and asks for their time. In figure B, all the other machine responds with their time, how far ahead or how behind they are from the daemon. The first machine responds with minus 10, the second machine responds with plus 25. In figure C, the daemon computes the average and tells each machine how to adjust their clock. It sends first machine plus 15 and second machine minus 20. In this way, Berkeley algorithm synchronizes the clock in different machines. Thank you.